Let's continue the ZEUS training with Section 15, Static, Aeroelastic, and Trim Analysis. And first we'll review the theoretical background of the trim module in ZEUS. So this is the problem statement of the trim analysis. The trim analysis solves a set of unknown trim variables and or trim degrees of freedom for the balanced 6-degree of freedom forces and moments about the CG between the aerodynamic and inertial loads. Now the trim variable vector can be expressed as A, where A is alpha, beta, P, Q, R, and delta, where alpha is the angle of attack, beta is the side slip angle, P is the roll rate, Q is the pitch rate, R is the yaw rate, and delta are the deflection angles of each of the aerodynamic control surfaces. The trim degrees of freedom vector contains the acceleration at the CG of the aircraft, which we denote as U_R, which is made up of nx, ny, nz, p dot, q dot, and r dot, where of course nx, ny, and nz are the accelerations along the x, y, and z axes, and then p dot, q dot, and r dot are the angular accelerations about the x, y, and z axes. And the net distributed loads on the structure are the difference between the distributed aerodynamic and inertial loads. So we have kgg times x equals fag minus fig. And here kgg is the g-set stiffness matrix, x is the structural deformation, fag is the g-set aerodynamic force vector, and fig is the g-set inertial force vector. Now the distributed aerodynamic forces fag is a function of the trim variable a and the structural deformation x. So we have the vector fag is the function fag of x and a. Now we assume that the trim variables can be split into the mean values and the perturbed values, a naught and delta a. So the distributed aerodynamic force can now be approximated by f naught g, which is a function of x, alpha naught, beta naught, p naught, q naught, r naught, and delta naught, plus the partial derivative of f with respect to a, times delta A. So F naught G is the distributed aerodynamic force at the mean flow condition. In the trim module, the trim variable is called thick cam, and the initial values of alpha, beta, P, Q, R, and delta are specified in the trim flet bulk data card. And then partial F, partial A is the force derivative matrix of the trim variable delta A, where delta A is delta alpha, delta beta, delta P, delta Q, delta R, and delta delta. Next we have the distributed inertial force vector. The distributed inertial forces, Fig, are due to the acceleration of the rigid aircraft, U double dot, and the oscillation of the structure, X double dot. So Fig is mgg times x double dot plus u double dot, where mgg is the g-set mass matrix. Now, since this is the trim module, x double dot is equal to 0, because the trim analysis is a static aeroelastic problem that does not involve the structural oscillation. And of course, if x double dot is considered, then that is a dynamic loads problem. U double dot can be related to the trim degrees of freedom by the rigid body modal matrix phi rg. So U double dot is equal to phi rg times ur double dot. Now substituting equation 14.6 into 14.5 yields the final inertial force vector Fig equals mgg times phi rg times u double dot r. Now the trim module in ZEUS is solved using the modal approach. So now we substitute equations 14.4 and 14.7 into 14.1, yielding equation 14.8. So we have kgg times x plus mgg times phi rg times u double dot r equals partial f partial a times delta a plus f naught g. Now the modal approach approximates x as phi eg times qe, where phi eg is the elastic modal matrix excluding the rigid body modes, because the rigid body modes cannot produce internal loads in the structure. And just as a note, for a whole aircraft structure, normally the lowest 50 elastic modes are sufficient to achieve a converged solution. Now, plugging equation 14.9 into 14.8 and pre-multiplying the resulting equation by phi rg and phi eg transpose respectively gives equation 14.10. So the phi rg transpose times kgg times phi eg equals 0 because of the orthogonality of the rigid body and elastic modes. And then we have mrr times u double dot r equals phi rg transpose times partial f partial a times delta a plus phi rg transpose times f naught g. And then equation 14.11, we have kee minus phi eg transpose times mgg times phi rg. Once again, this term is 0. This is all multiplied by qe, and this equals phi eg transpose times partial f partial a times delta a plus phi eg transpose times f naught g. Now mrr is phi rg transpose times mgg times phi rg. That is the 6x6 rigid body mass matrix. So this rigid body mass matrix is a user input in the trim bulk data card. And then KEE equals phi EG transpose times KGG times phi EG. This is the generalized stiffness matrix of the elastic modes. And this is computed by ZEUS based on the imported KGG or KGH matrix. Now it's best to import the KGH matrix because the KGG matrix, of course, is a full matrix, which would be very, very large. But in Nastran, you can compute the KGH matrix and then output the KGH, import KGH into ZEUS. Equation 14.11 is the static aeroelastic equation. It can be solved for partial f partial a and f naught g. And 14.10 is the trim equation and is solved for the trim variables. So now we have the static aeroelastic analysis for computing partial f partial a and f naught g. So f naught g is computed at alpha naught, beta naught, p naught, q naught, r naught, and delta naught using the pseudo time domain aerodynamic computation option in the Euler solver module. This provides the distributed aerodynamic forces for the trim variable thick cam, and it also establishes the mean flow solution. Next, partial f partial a is generated using the pseudo time domain aerodynamic computation option in the Euler solver module for each trim variable. So for n trim variables, it requires n static aeroelastic analyses. And we have two options available for computing the partial f partial a. First is the finite difference method using the full Euler solver, and secondly, we have the linearized Euler solver. Next, we have the trim equations. So the right side of equation 14.10 contains the aerodynamic stability derivatives with the structural flexibility effects. So this f bar r equals phi rg transpose times partial f partial a, which equals q infinity times s times the aerodynamic stability derivatives as shown here. And then the f naught r is phi rg transpose times f naught g, which is equal to this quantity. So these coefficients can be replaced by the user supplied values obtained by a wind tunnel test. In general, equation 14.10 can now be written as shown here. MRR times U double dot R equals F bar R times delta A plus F naught R. Now splitting U double dot R and delta A into the given set and the unknown set, respectively, yields the trim equation. So U double dot G is the given set of U, and U double dot U is the unknown set of U. And then delta A we split into the alpha or A given and A unknown. So that gives us equation 14.15. So we're just rearranging terms so that we have the unknown and the unknown on the left-hand side and the given on the right-hand side. And so this leads to either a determined or overdetermined trim system. So if the total number of U double dot unknown and A unknown equals the number of trim degrees of freedom, then equation 14.15 can be solved by directly inverting the left-hand side matrix. So this equation is called the determined trim system. However, if the total number is less than the number of trim degrees of freedom, then the trim equation is called the underdetermined trim system and is unsolvable. And then finally, if the total number is greater than the number of trim degrees of freedom, this trim equation is called the overdetermined trim system. Now, to solve the overdetermined trim system requires the minimization of an objective function while subjected to a set of constraint functions. So for example, you can maximize the roll rate of an active aeroelastic wing that has 4 control surfaces on each wing, while the hinge moments cannot exceed a design value. Another example is minimizing the wing root bending moment of a joined wing that has 3 control surfaces on each wing, while the control surface deflection must be within upper and lower bounds. So the optimization procedure for the overdetermined trim system is described here. So the general optimization problem is formulated as we have an objective function obj of x, which we would like to minimize, and then it's subjected to the constraint functions gj of x is less than 0 for j is 1 to n. So we have n constraint functions, and then x is the design variables, that is u and au. Now the trim module requires the user to define a set of trim functions, such as section loads, grid point displacement or forces, element stress or strain, aerodynamic forces and moments, etc. And the trim functions can be selected as the objective function and constraint functions. So our objective function of x equals the sum of ci times fi, where ci is a weighting factor, and then fi are the trim functions that we've defined. Our constraints, we have fi of x must be between fi min and fi max, and then our unknowns as well are constrained to be between a minimum and maximum values. Now some of the trim functions require additional input via the assigned matrix, executive control command, or the DMI bulk data card. For example, the grid point inertial forces needs mgg, and then the element stress or the modal stresses need sigma e, and then mgg and sigma e can be provided by the structural finite element analysis. Next, we'll review the trim iteration procedure of ZEUS. So equation 14.15 is a linear trim equation in which all aerodynamic stability derivatives are assumed to be constant. That is, they're not dependent on the mean flow condition. However, in real flow, the stability derivative is a function of the mean flow condition. For example, CL alpha is actually a function of alpha naught, beta naught, etc. And the Euler solver with the boundary layer coupling can capture these nonlinear flow characteristics. So, the trim module employs an iterative procedure that iterates around the linear trim equation to search for a converged solution. So at each trim iteration, the trim solution is used to update the mean flow condition. The aerodynamic stability derivatives are based on the updated mean flow, are recomputed for the next trim iteration, and then the solution converges when all the trim variables are small. So we start with the initial mean flow condition. So we have alpha naught n, beta naught n, etc., where n is 0. Then we go to the Euler solver module. So we have the pseudo time domain aerodynamic computation, the mean flow solution, and the aerodynamic stability derivatives at the mean flow condition. Now with these stability derivatives, we can solve the linear trim equation. So that solves for delta alpha, delta beta, etc. And then we ask the question, are all of the trim variables small? So usually for the first iteration, that would be no. So we move to the next iteration, and then we update the mean flow condition. So alpha naught at time step or trim iteration n plus 1 equals alpha naught n plus delta alpha. And we do the same thing for all of these variables. And then we redo the Euler solver module with the new mean flow condition. And then recalculate the aerodynamic stability derivatives. And then once again, we'll solve the linear trim equation. So once we've converged our solved delta, alpha, delta, beta, and so on will all be small values. So when we ask the question, are all trim variables small? We'll say yes, so that is our trim solution. So our alpha naught n, beta naught n, and so on is the solution of to our trim equation. So once we have the trim solution, we can calculate the modal displacement, sectional loads, and loads in terms of the Nash-Rand force and moment cards. Now the number of trim iterations is capped at 3, but this can be altered by the param card with the entry max trim. So we found that usually 3 trim iterations is enough to calculate the trim solution. However, if you would like to, you can increase the number of trim iterations, but remember, we always do this test, are the trim variables small, so the trim iteration procedure is allowed to terminate before reaching the full 3 iterations or whatever you define as max trim. So let's go through next the bulk data cards that we have in ZEUS. So we have the trim card, which defines the flight condition, the rigid body mass matrix, the trim degrees of freedom, and the trim variables on which to perform the static aeroelastic trim analysis. That will call out to the MLD trim card to export the trim solution, and then the following trim cards, which we'll review. Finally, the plot trim can be used to generate a file that contains the flight loads in terms of the Nash-Rand force and moment cards at the structural finite element grid points. So the user can insert this file back to the finite element model to perform a static analysis for detailed stress calculations at the trim condition. This is the bulk data in relationship. So we have the trim card is referred to by the trim case control section. The trim card refers out to an MK Aero Z card to define the Mach number and mean flow condition. The trim card refers to the trim var cards to define the trim variables. The trim var can optionally refer to trim link to define trim variable linking. Meanwhile, for the overdetermined trim system, the trim card can refer to the trim objective and trim constraint cards, which then refer to the trim function cards. And then the trim can refer to a set 1 card to measure the loads at the trim condition. So here's the trim card. We have the ID. Next we have the ID MK field, which refers to the MK Aero Z card. QInf defines the dynamic pressure. Now in the trim card, the analysis units for trim are the same as the model units. You cannot change the analysis units like you can for the flutter analysis and the transient analysis. So that is one restriction. So this QInf must be in the model units. Next, for the overdetermined trim system, we have the ID OBJ and the ID constraint fields, which refer to the trim objective and trim constraint bulk data cards. Next, we need to define the CG location. So we have row X, row Y, and row Z. And this is relative to the aerodynamic reference point defined in the Aero Z card. Next, we have a weight mass field. So this allows you to convert weight to mass. So if your weight and inertia terms here are in terms of weight, then you need the weight mass to convert that. So for example, if you're in English units, your model is in feet, and then your weight here is in pounds, and your inertia terms are in pounds, the weight mass would need to convert the pounds to slugs. But if you're doing using SI units where your model uses meters and kilograms, and so your weight field is actually the mass, and then your inertia terms are all in terms of kilograms, then weight mass would just be 1 because the remaining terms are actually mass. So this weight field is the total weight or mass of the aircraft, and then IXX, IXY IYY, IXZ, IYZ, and IZZ define the 6x6 rigid body mass matrix MRR. The next row of the trim card, we define the trim degrees of freedom. So the TRN ACC is a flag, a character vector, which can either be true or G. So if it's G, our NX, NY, and NZ are in terms of G's. So for a simple 1G cruise condition, you can set TRN ACC to the character string G, and then NZ would be 1. If you want to define these acceleration in terms of model units, then you can set TRN ACC to be true. So for example, if you're using kilogram and meters as your model units, and you want to do a 1G cruise, then NZ would be 9.81. So NX, NY, and NZ are the trim degrees of freedom, X, Y, and Z accelerations, and then P dot, Q dot, R dot are, of course, the accelerations P dot, Q dot, and R dot. And then lastly, the load set field refers to a set1 card to define a set of trim functions, which ZEUS will calculate the value of and print those out in the output file. And then lastly, our open-ended input are the trim variables, which define the vector A. So ID var refers to the trim var bulk data card, and then the value defines the value of that trim variable. So the value can either be free or it can be a real value to fix the value. So for example, if you want to do use the trim analysis to calculate what the loads are if the angle of attack is fixed to be 1 degree, then this ID var could refer to the trim var card that defines alpha as your trim variable, and then your value you would set to 1. However, if you are doing a trim analysis where you want to say I'm at a 1G cruise and I want to calculate what my alpha, my angle of attack is, and what my elevator are, then the ID var would be, this would refer to the trim var card that defines alpha, and the value would be free. Your second one would refer to the trim var card that defines your elevator, and then value would be free. So here's an example of the trim var card, or the trim card. So we have our weight mass conversion in here, 0.031. Then we have our weight, and then our parameters defining the mass matrix here. You can see the CG location we've defined. This is an overdetermined trim, so we refer out to the trim OBJ and trim constraint. Dynamic pressure here is 1200 psi. And let's see, our trim degrees of freedom, the units are in G's. So NX is none, so we're excluding the X direction. NY is 0, NZ is free, so we're going to calculate what NZ should be. P dot is 0.2, Q dot is 0, and then R dot is free. So you can see that we're specifying some of the trim degrees of freedom, and then some of them we're leaving as free, and then one of them, NX, we're excluding from the analysis. So we have just 5 degrees of freedom here. And then our ID var, we'd have to look at the definitions of the trim variable cards, but you can see for this one, we specified it to be 25. This one is free, this one is free, and this one is free, and then these are specified. So we have 1, 2, 3, 4, 5 free variables, and we have 5 constraints. Okay, so actually the trim objective and trim constraint fields are going to be ignored because we have 5 free variables and a total of 5 trim equations. So the MRR is defined in the second row. This must define the full span model, the mass values should describe the full span model, even if a half span model is used for the aerodynamic model. Okay, so next we have the trim var card. So we have an ID, which is referred to by the trim card, and then we have the label field. So we have three types of trim variables. So the first is the program assigned trim variables, where we have alpha, beta, P rate, Q rate, R rate, and thick cam. Next we have the control surface type of trim variables. So the label must match the label in an AE serv Z, AES link, PZT mode, jet force, and grid force card. Actually, I believe jet force is not present in ZEUS. That's left over from ZEUS. And then lastly, we have the user-defined trim variables. So here, if the label does not match any of the program assigned or the control surface type of variables, then it's a user-defined trim variable. So for the user-defined trim variables, then the user must specify the sim and then the user-supplied stability derivatives. So let's continue on with the trim var card. You can specify lower and upper bounds, which are only used in the overdetermined trim system. Then the trim link allows you to link to other trim variables. The DMI imports the distributed aerodynamic pressure derivatives to replace the ZEUS computed values. Sim defines if this is a symmetric, anti-symmetric, or asymmetric trim variable, and this is only used if we have a user-defined trim variable. And then the initial field defines an initial value for the optimization in the overdetermined trim system. And then lastly, we have the user-supplied stability derivatives, which you can optionally specify to replace the ZEUS computed values, or in the case of a user-defined trim variable, you must specify all 6 values. So in this case, we have alpha as our trim variable, and the DC alpha, or alpha CD, or the derivative of alpha with respect to CD, there we go, alpha CD, we're overriding the ZEUS computed value with our value of 0.01. The remaining stability derivatives, we specify none, so that ZEUS will use the ZEUS computed values for alpha in this example. Next we have the plot trim bulk data card, which can be used to plot the deformed aerodynamic model. So here we've plotted the original surface panel model and the deformed model together. So the original model is the blue, and then the deformed model, which would be the output of the plot trim card, is in red. And then the second option, you can export grid point forces in terms of Nastran force and moment cards, and then the user can insert this file back into a Nastran input deck for a detailed stress analysis. So this is the top of the example here. So you can see we output some comments in the file that tell you where this file is coming from. So these are the analysis parameters. And then we have the force and moment cards as shown here. Next, we'll look at a sample case for the trim analysis. So this is a forward swept wing with a canard configuration. So this is the surface mesh with the control surface and the gap definition. So we have the canard defined here, we have the wing defined here, and then we have a gap card here to assist with the mesh generation. And then we have the structure model shown up here with the grid points. So we've got, also we have a control surface. So the TE flap control surface is shown here. That's defined by this AE serv Z card. The canard right here is defined by this AE serv Z card. We have our C-Aero7 for the wing. We have the airfoil shape. We have the C-Aero7 for the canard. And then we have the gap defined in here. So this is the resulting mesh. So you can see our gap card in here assisted with the mesh generation, and then this is the resulting mesh. And the top-down view, This is from the back looking forward. So this is our mesh, and this is the side view. From the side view, the lines are all, it looks bad because we have, you're seeing all of the grid lines lying all on top of each other from the side view. So you can see that because of the sweep angle, we've got what appears to be grid lines crossing each other, but they're not. To get a good look at what the mesh actually looks like, if you just look at the top-down view and then from the back, that will give you an idea of what the mesh looks like. And then here is the full 3D view. And then our two Y zones we had defined. Y zone 1 included the canard, and then Y zone 2 is the outboard portion of the wing, not including the canard. So this one block card here generates this 3D mesh. So once again, because we don't have a fuselage, we just have the Aero7s, the input is extremely easy to set up. Next we have the spline. So we're using the spline 2, the beam spline for the wing, and then we're using attach for the canard. So we're attaching the card to a reference grid point. And here's an example plot mode output. Next we have the executive and case control sections. So we're importing the Nastran solution with assign FEM, and then we're importing the MGH matrix with the assign matrix executive control command. And we have two trim subcases. The first is a symmetric 1G level flight. This is a determined trim system with 2 trim variables. And then we have the symmetric 1G level flight with the overdetermined trim system with 3 trim variables. So the first subcase, symmetric 1G level flight at Mach 0.9, Q infinity of 1200 psi. Our 2 trim degrees of freedom, our NZ is 1G, and then Q dot is 0. The 4 trim variables, our Q rate equals 0, thick cam equals 1, so we're setting these, and then canard is free and alpha is free. So we have the 2 trim equations and 2 free trim variables. The MK Aero Z card defines the Mach number and generates the mean flow condition shown here. So the trim card will refer to this MK Aero Z card. We have 5 trim variables. So the control surface trim variables, we have trim var 600, which is the canard. The trim var 1000 is trailing edge flap. Now these limits will be ignored for the determined trim system. Then we have a trim link here. So we're alpha is linked to the trailing edge flap. So this trim link refers to the trailing edge flap, and then the alpha refers to the trim link here. So our program assigned trim variables are Q rate, thick cam, and alpha. So what we're doing here is scheduling the trailing edge flap based on alpha. So if we're at alpha of 1 degree, then our trailing edge flap will deflect by 1 degree. And then this is our trim card. So we're referring to the MK Aero Z. We define the dynamic pressure. The CG is defined here. So the CG location is calculated based on rho X, rho Y, and rho Z, and the aerodynamic center defined in the Aero Z card. So this is our Aero Z card, where ref X is 15, ref Y and ref Z are 0. So the final XCG is rho X plus ref X. So we have 2.27607 plus 15. YCG is 0 plus 0. And ZCG is 0.0310559 plus 0. Our WT mass is 0.031081, which converts the weight in terms of pound mass to slugs. Well, the weight would be pound force, the mass. The weight, there's 2 ways to look at it. We're defining our weight in terms of pound force, or we're defining our mass in terms of pound mass. in the end, it's the same thing. Then we have our TRN ACC is true. So our NZ, which we want to be 1G, is 32.175 feet per second. Our TRN ACC is true right here, and then NZ is the 32.175. Q dot is 0. And then the load set 100 right here refers to a set 1 card to list the ID of the trim function card for the trim function solution output. So the set 1 with ID 100 refers to 10, 20, and 30. So these are the 3 trim function cards. And then the total number of free trim variables is 2. The trim degrees of freedom is 2. So this is a determined trim system. So our ID constraint and ID objective are both 0 because we don't need them. So the 600 here is free, 800 is free, and then the 500, let's see, we got to go back and look. What was 500? 500 was thick cam. Okay, so you always want to include the thick cam trim variable and specify the value to be 1, because remember, that is your mean flow solution. So always include thick cam and always set the value to be 1. Next we have 600. Let's see, 600 was canard. So canard is free, so we're going to solve for the canard. Next we have 700. 700 is Q rate. So we're setting that to be 0. And then 800 is alpha. And alpha is free. So this is the interrelationship of the trim cards for this subcase. So we have the trim referring to our trim var cards. The trim var 800 refers to the trim link, which refers to the trim var 1000. So remember, we're scheduling the trailing edge flap based on alpha. And then our trim functions, we have 2 load mod cards and then stress in a bar element. And then the trim refers to the MK Aero Z. So we have the 3 trim function cards here. So the first trim function, we're defining its type to be load mod. So our load mod is Y moment. So this is the hinge moment of the right hand side aileron computed on the aerodynamic boxes. So no inertial loads are included. So our comment here is the hinge moment, the right hand side aileron. Next, trim function 20 refers to load mod 101. That's the bending moment of the right-hand side wing, including both the aerodynamic and the inertial loads. So the trim function type is FEM, which includes both inertial loads and aerodynamic loads, referring to the load mod card here. And so this load mod card refers to this set 1 defining these grid points. So we're including the inertia of these grid points and the aerodynamic boxes to define the right-hand side wing. And the next, trim function 30, refers to the modal stress at a C-bar element of 110 of the FEM model. The modal stresses are obtained by activating stress all in the Nastran analysis, and these stresses are input by the DMI equals S-bar 110. So this is our stress at C-bar 110. This DMI defines the modal stress for C-bar 110, so we've obtained these values from Nastran. Okay, next we have the output, the ZEUS output. So the first trim iteration result is shown here. So we have this header here, the nonlinear trim analysis at iteration number 1. So first we have the static aeroelastic trim analysis with the trim variable thick cam. So the mean flow solution thick cam is generated using the TRM step equals 100 specified in the MK param card. And actually we left that blank, so we use the default, which is 100. So we can see the convergence of the lift coefficient here converges after 100 steps. Then we move on to the static aeroelastic trim analysis with the trim variable canard. These only use 33 iterations. So we have the param called trim reduce, which is by default 3. So we take the trim step, which is 100, and divide by trim reduce 3, which leaves us with just 33 iterations. So we use the 33 for the remaining trim variables other than thick cam. So canard, alpha, and so on. Well, in this case, we only have those two, canard and alpha. Then we print out the table here of our stability derivatives. So for thick cam, so this would be CD naught, CY naught, CL naught, and so on. Now because this is a symmetric analysis, this column is all 0, this column is 0, and this column is 0. And then we have our alpha, so this would be CD alpha, CL alpha. We have Q rate, and we have canard. So then we print out the trim solution. So the computed alpha is 0.07 degrees, and the computed canard is 1 degrees. So that is not small yet, so we move to the second trim iteration. So now we've got, we recompute thick cam with our updated alpha and canard. So once again, we have the converged lift coefficients. Then we compute canard and alpha once again. This is our new stability derivatives. And then we solve the trim equation again. Now our computed alpha is 0.001 degrees. Our computed canard is minus 0.008 degrees. So the values of these trim variables are small, which indicates the trim iteration has converged. So now we compute the final trim solution. So we print out our CD, CY, CL, CR, CM, and CN. So we have the flexible values printed out here. We then print out the modal coordinate solution. So this is the static aeroelastic deformation of the aircraft, and then the values of the trim functions. So we remember we had the hinge moment of the right-hand side aileron, the bending moment of the right-hand side wing, and then the stress at C-bar. And then the final trim solution after 2 iterations is printed here. So our thick cam, remember that was restricted to be 1. Alpha is 0.07 degrees. Q rate, that was a user input, is 0. And the canard, which is computed by the trim module, is 1.035 degrees. And then we have the final forces and moments at the trim solution output here. Now we will compare the trim results for the full Euler solver of ZEUS, the linearized Euler solver of ZEUS, and Z-Aero. So if we take the thick cam variable, if we look at the drag, obviously Z-Aero gives us an almost 0 value. Then the ZEUS full and ZEUS linearized agree very well with each other. CL naught, once again, ZEUS full and ZEUS linearized agree well with each other. Then we have the Z-Aero solution here. And then we have CM naught here. Next, we've got CL alpha. So CL alpha compares pretty well between Z-Aero and ZEUS. CM alpha, we also have a pretty good comparison between Z-Aero and ZEUS. CL canard and CM canard are shown here. Now the trim solution is going to depend on these aerodynamic stability derivatives. So because of the differences in our values here, we're going to expect the trim solution to be a little different between ZEUS and Z-Aero, which indeed you can see Z-Aero calculates a larger canard deflection and a little bit larger angle of attack. Meanwhile, if we compare the ZEUS full Euler solver and the ZEUS linearized Euler solver, these two solutions are very close together. And then our trim function results, now because we're at a slightly different angle of attack, we would expect the loads here to be different, which indeed they are different between ZEUS and Z-Aero. So the hinge moment is here. The root bending moment on the wing values are shown here, and then the stresses on a C-bar element are shown here. Next, we'll move to subcase 2, which is a symmetric 1G level flight with 2 control surfaces now. So we're going to remove the trim linkage on the trailing edge flap, and now we're going to solve for the angle of attack, canard, and trailing edge flap subject to some objective function. So we're going to use the induced drag as the objective function to be minimized. So that is done through this trim objective bulk data card here. So the trim function here is measuring CDL, and so this trim objective is simply referring to this trim function, and we're going to minimize this. And then also we're going to define the absolute hinge moment on the trailing edge flap to be less than 900 foot-pounds as the constraint function. So if we take the hinge moment of the trailing edge flap and square it, it needs to be less than 810,000. So that this 2 here means we're squaring that trim function, and then we need it to be less than 810,000. And this is the trim card. So now we're referring to the objective and constraint, and then we have 810 is our trailing edge flap, and that is set to be free. And then the remaining, everything else is the same as the previous analysis. And so this is the interrelationship. So we have the new trim var. So this is the non-linked version of the trailing edge flap. And then we've got our objective and constraint functions here. Okay, so now we have the output. So this is the objective function and the trim function results. So we have the CDL here. So our function value is printed out, and then the objective function is the objective function value based on that is printed out. And then also we've got the stress in the C-bar. It looks like that was also included in our objective function. And then if we look at our constraints, the constraint value was 810,000, and the calculated is actually 811,000. Now, just due to the solver method in ZEUS, sometimes the constraints are not strictly met, but they are almost met. So you can see that our constraint value is 810,000, and our computed value is 811,000. So technically our constraint is not satisfied, so we have no, but it is almost satisfied. So my recommendation is if you have a hard constraint value, just multiply it by about 95% and then use that as your input constraint value in ZEUS, and then that will make sure that you satisfy your actual constraint. So this is just due to the solver method in ZEUS. It is allowed to bust the constraint by just a little bit. And then we have the values of the trim functions printed out next in the ZEUS output. So we have the hinge moment on the right-hand side aileron, the bending moment of the wing, and then the stress in the C-bars. And then continuing with the output, after the trim iteration converges, the trim module performs a final static aeroelastic analysis. So we add all the trim variable solutions to the initial mean flow condition and then compute the aerodynamic force and moment coefficients in both the body axis and the wind axis. So our computed alpha is now minus 0.2 degrees. Our canard is 1.6 degrees, and our trailing edge flap is minus 1.1 degrees. And then this is our final aerodynamic forces and moments in the body axis and the wind axis. Once again, we'll compare the results for the ZEUS full Euler solver, the ZEUS linearized Euler solver, and then our ZEUS results. So ZEUS, once again, agrees very well with itself. the two different solver methods, which differ slightly from the zero results. And when we look at the trim solution, our alpha is very close between the full Euler, linearized Euler, canard, and TE flap, and then zero is different. If we look at the trim function results, we can look at our hinge moment due to the aerodynamic loads on the right-hand side aileron. We, for the ZEUS, we are right at our constraint. And then for the root bending moment on the wing, we've calculated these values, and our stress in our C bar is here.